Okay. Okay, so where we are in chapter 6. Chapter 6 is on solving a system of equations. Okay, so what do I mean by system of equations? Let me write down an example of a system of equations. So chapter 6. Simultaneous algebraic equations. Okay, to make our life easy, we'll only be dealing with linear equations. The non-linear equations can also be solved, but you need some more advanced techniques. So I should add here linear. Okay, so what does a system look like? A system of equations looks something like this: a11 x1 plus a12 x2 plus so on, a1n xn equals v1, a21 x1 plus a22 x2 plus so on, a2n xn equals b2, and just keeps going till, let's say, an1 x1 plus an2 x2 plus so on, ann xn equals bn. Okay, so if you just count 1 all the way to n, you'll see that there are n equations. Okay, what are some of the things in the equations? We have aij, where I goes from 1 to n, right? It's like a11, a12. J also goes from 1 to n, so I can just write it as j n. These are constants. Similarly, we have bi, where I goes from 1 all the way to n. These are also constants. And the xi, where I goes from 1 to n, are typically the unknowns, something we need to solve for. And looks like w n n, yeah. Now it turns out that this set of equations can be written as God, this got hung. It's fine. Ax equals b, where a would be something like this: a11, a12, so on till a1n, a21, a22, so on till a2n. Keep going left, right, up to down. an1, an2, so on till ann. B would be b1, so on till bn, b1. Maybe I should put one more, b2. And then x are the unknowns: x, x1, x2, so on till x x2 xn. Okay, again, capital A is a constant matrix of size n by n. Write that down. N cross n. This is n cross 1, n cross 1. Okay, so we're looking at methods to solve for x. This is given, and this is given. Okay. So there are a couple of methods, and really what we're going to do is use those methods to solve for x. And for the exam, you pretty much can expect that you'll be asked for one or other method to be used. And same for your homework. So let's look at a method known as Gauss elimination. Yeah, I'll give you a simple example to motivate this. If you have a 2 by 2 system, what I mean by 2 by 2 is there are two equations and two unknowns. A's, B's are constants. X1, X2 are unknown. Okay, so that system, I'm sure all of us have done probably in high school or something, right? How do you solve that? Well, each equation is dependent on the other, right? That is, x1 and x2 appears in both equations. And one way you could do this is you could solve for x1 in terms of x2 in one of those equations, and then substitute that in the second equation. And there you have solved for x1, x2. That's something which we do. Now, we want this to, whatever we do, we want that to generalize to, imagine 100 equations, 100 x's, 100 equations. How do you solve that? So this method, which I'm going to talk about, sort of has a method which we can extend to a higher dimensions. So what we do is use first equation, use A11 in 1 to eliminate x1 in 2. Okay, so if I want to do that, what I have to do is I need to rewrite equation 2 in the following way. I take equation 2, I subtract the ratio of A11 divided by A21, and then I multiply, sorry, my bad, A21 divided by A11 and multiply it with 1. Okay, so this is probably something you've done before. You substitute x1 in terms of x2. This is just another way of saying the same thing. You're eliminating one of those constants by using one of those unknowns using the first equation. So if you do this, what I'll get is, by the way, I forgot to say, you could take any of those equations, multiply any equation with a constant. Like you'll have to multiply the left side and the right hand side of this equation with the same constant, and it will not change the equation. It will keep the equation the same. Okay, that fact is exploited in this thing which I'm doing here, which is I multiply equation 1 with a constant. This is a constant. And multiplying an equation with a constant both sides doesn't really change its its significance or its nature. It keeps it the same because you can divide that factor out. And then if you take one equation and subtract from the other, it really doesn't change anything. So we are exploiting that fact. So if you do this, then what you'll see is equation 1 will stay as it is. We're not doing anything with it. Stays the same. And then the equation 2, we have to do 1, which is I'm just going to do exactly this over here. This is my new equation. This is the old one. So my new equation, which I'm going to write down here, is the old one, which is a21 x1 plus a22 x2. I'm going to write it in such a way that there's some space for me to write the subtracted part. Okay, so b1. So this is my first equation, or equation 2, old. No, it's 6. Sorry, my bad. Equation, this should be 2, right? 2, and all looks good. Now I do this a21 divided by a11, and then I write equation 1. Yeah, I will never write it again. I just want to write it down so that you understand what's going on. We'll just not do this ever again. We'll just directly write the answer to, as you'll see, to the example problems I solved in class. So if you do this right, then you'll see that this coefficient a21 will cancel, or a2x1 will cancel off with this, right? When you multiply it together, you'll see a11 canceling off a21. So a21x1 will cancel the a21x1, and so you'll be left with a22x2 minus a21 a11 a12x2 equals b2 minus a21 a11 d1. In fact, I can just pull this out. Okay, and here you have solved for x2. This is your x2, and then once you get x2, it's just a matter of substituting x2 back in x1. This is known. Sub in 1 and solve for x1. Okay, let's see how to do this in a higher dimension. Okay, instead of trying to write those coefficients and get confused, I will just show you what is the pattern which emerges. And once we understand the pattern, we can easily extend it to higher dimensions, either in software, in writing code, or by doing, or if you want to do it by hand. Okay, so this is how Gauss elimination works. Pattern. So we have a11 x1 plus a12 x2 plus so on till a1n. I'm just going to write 2 equations. Maybe I'll write 3 plus a22 x2. Okay, let me just skip this. I don't need this. I just need the first. We write the first 3. Okay, that's good enough. This is an error. This should be 2, 1. Second row, first column. Third row, first column. This should be x1. My bad. x1 plus a32 x2 plus a33. You know what? We just, I'm going to do the same thing, but let me write in the way that it is. You see the pattern. We just use this grids to write it better. A12x2, A22x2, A32x2 plus A13x3 plus A23x3 plus A33x3 plus so on, P1, P2, P3, and then this just keeps going on till an1x1 plus an2x2 plus an3x3 plus so on equals Pn. Okay, the first step is so there are pretty much n steps. First step, use A11 to eliminate x1. We call this 1, 2, 3, so on till n, to eliminate x1 in equations 1, sorry, 2 through 2, 3, so on till n. Okay, so what you're doing here is you're taking this to eliminate x1 in column in equation 2, x1 in equation 3, and so on till equation n. For that, what you'll do is clearly you will take the first equation, you'll divide it by A11, so you have 1 there, and then multiply with A21, so something like A21 A11 times equation 1, so equation 2 minus that, equation 3 minus A31 A11 times 1, and so on till equation n. Just let me be consistent. I'm sorry about this. I should maybe write this as 1. I was not writing 1 and 2 because I think I wrote down the previous page, but I think this will make it super clear when we try to generalize this. This is just Pn. So 2, 3 minus n minus a. Okay, so you see what you're doing? You're rewriting equation 2, equation 3, equation n by using A11 in this fashion. A21, A31 are coefficients of the first row. So what will happen is eventually x1 will drop out from all the equations but the first one. So the result of this calculation is we have the first equation will remain as it is. The second equation will not have any x1 because we eliminated it. So I'll call that a12 prime x2 plus a13 prime x3 plus so on equals b2. This should be a22. Sorry, this is a23. Yeah. So this will be a32 prime x2 plus a33 prime x3 plus so on equals b. This will be b prime, b2 prime, b3 prime, and so on. And 3 prime x. Okay, so let's see, no x1. Okay, now what you find is that you're left with n minus 1 equations. These are your n minus 1 equations. Okay, what you can do is you can play the same trick as you played on the n set of equations. You will eliminate x2, use this element, the first, second row, in this case second row, but first for the n minus 1 system of equations, and eliminate x2 in every row till you reach the nth row. Okay, so when you do that, you'll end up. So let me write that down. Not spend overly too much time on that. So use an2 prime in, let's just give it a name. Let's call it 2a, 3a, so on till na into a to eliminate x2 in equations 3a, 4a, so on till na. And so I just write one more step, and then I think we'll get the idea. So the first equation remains as it is. The second equation now has changed, but because the second step, it will not change after the first step. So this will remain a22 prime x2 plus a23 prime x3 plus so on equals b2 prime. Now everything below this will not have an x2, so there will be a33 prime double prime x3 plus so on equals b3 prime. There will be a43 x3 plus so on till n3 prime x3. This should be double prime, just indicating that it was modified as a result of the second step. So you see what's happening? We are slowly getting a pattern, which is after step 1, there was no x1. After step 2, there's no x2 here. Okay, so if you keep doing that, you'll clearly see that after trying n times, after n such steps or iterations, we will get something like this: a11 prime x1. Sorry, my bad. First row remains unchanged. Next one would be a22 prime x2 plus so on. Next we'll have the first one would be a32 prime, just right here, a13 x2 x3, a23 x3 with a prime. This will have a double prime x3 and so on till we reach n primes. So let's put n xn equals pn n p. A row before that would have two of these. So an xn minus 1 plus a n minus 1 n a n minus 1 n minus 1 n minus 1 n minus 1 p3 double prime b2 single prime p1. Okay, so the key thing is no x1, no x2, no x3, so on till here we'll have no xn minus 1. And so this last equation can be used to solve for xn, because that equation has no x1, no x2, so on till xn minus 1. So once we solve for xn, we can sub that value in here and solve for xn minus 1, because this equation, remember, has only two unknowns, xn minus 1 and xn. And then we just go, once we have those two values, we can go one above that, solve for xn minus 2, and just keep doing up. So there's one step where we go down, eliminating eliminating the lowest order coefficients, so x1, x2, x3, so on. And then once we get that, we are able to solve for xn, then xn minus 1, then xn minus 2, and so on. So let me just write this down. So when you refer it, you know what we're doing. From the last equation, solve for xn, use from let me call it I don't know, n raised to n, because you did n times. Use xn in the second to last equation. N minus 1. This if you're getting confused with this, ignore this. But it's the second to last equation, and solve for xn minus 1. And then you'll use xn minus 1. That is the two values you obtained before in the third to last equation, and solve for xn minus 2. So you keep doing that till you can solve for so last step would be use xn minus 1, xn minus 2, xn minus 3, so on till x2 in the first equation, in the first equation, to solve for x1. So this completes it. Then you do it number of times. Look at this. So here we are solving for xn, then xn minus 1, then xn minus 2, so on till x1. So you see, you're going backwards. We're getting the solution in backward fashion. Okay, let's put this to practice. Let's solve a problem where we do this for a 3x3 system. At the most time, we go up to level to 4 equations in the exam. I don't think I can give you more than that. Just it's not worth the time, right? It's going to be hard to do it. I'll also show you code which does this. So I'll write a system of equations. We'll use the Gauss elimination, the way I've described it, to solve for it. One thing I should mention before I go, you'll hear this terminology called a pivot. These are called pivots. This is a pivot. It was used in order to eliminate all the x's. After the first round, this was the pivot. It was used to eliminate all the x2s below it. And then we had this was the pivot, and so on, right? So you see that these pivots are always on the diagonal of that reduced system. Okay, so here is a problem. Example 1. Solve the following set of equations using Gaussian elimination. Okay, so this is a 3 by 3 system. 2x1 plus x2 plus x3 equals 7. x1 minus 3x2 plus x3 equals minus 2. 2x1 plus 2x2 minus x3 equals 3. Okay, now for this system, you could technically use the same method, keep x1, x2, x3, but I'm going to show you a technique where it's actually much easier to keep track of numbers without really writing x1, x2, x3. It just makes life easy. It avoids clutter. Just think of the clutter which was here in keeping all the x's. The fewer the variables we keep, the better it is. So there's a lot of clutter in these equations because I keep x1, x2, x3. I'm going to show you where you don't have to keep track of x1, x2, x3. So what we'll do is, in order to solve this, we'll use this notation. We'll write only the coefficients of x's in a matrix format. So the coefficients are 2, 1, 1. That's from the first row. Then we have 1, minus 3, 1. And then we have 2, 2, minus 1, right? So just the coefficients. And then we'll write the coefficients of the right-hand side, which is 7, minus 2, and 3. Okay, and just to make it look good, I'm just going to draw this just to show that this is our A, if you like, and this is our B. Remember, we are trying to solve AX equals B. So what we'll do is we'll try to reduce this equation to this format. Okay. So you see that these will be the pivot elements. Everything below this is 0. This is a 0, 0, 0. Okay, so we'll use those pivot and those things, operations I mentioned, to reduce it in this format. And then we'll see that the last equation, since this is a value which is known, this is a value which we've got, we can just compute this value by just doing this thing over here divided by the thing on the right. It'll be clear when I do it. But we're trying to get to this goal of reducing it to this form. Okay, so let's proceed. Let's get this and go from there. And you see it doesn't take too much time or space either. Two, 1, 1, 1, minus 3, 1, 2, 2, minus 1, 7, minus 2, 3. Okay, so first step, our pivot is 2. Our goal is to use the pivot to eliminate 1 and 2 in the first column. So we see that in order to do that, my new row 2, this is row 1, row 2, row 3. So new row 2 will be my old row 2, which is this one, minus I take the pivot, I divide by the pivot, and then I take this element, put it here, times R1. So this is my old R2, this is my new R2. So usually I will just do both steps to eliminate 1 and eliminate 2, but here I will break it into 2 so that you'll see how it goes. So if I do this, we have the old, I'm just going to do this operation, write it down there so you see step by step. Row 2 is 1, the old one, minus half of row 1, which is 2. Second one, we have minus 3. You keep it as it is, row 2, minus half of row 1, which is this one. Then we have 1, old row 1, row 2, minus half of first row. And then minus 2, minus half of row 1. Okay, everything else remains the same. Okay, now you don't, as you do this faster, you don't have to do this the way I've drawn it. You can just figure it out in your head and write it down, or use a calculator to figure it out and write it down. So what you get here is 2, 1, 1, 7. First row is unchanged. Second row will become 1 minus 1, will be 0. Minus 3 minus 0.5, so minus 3.5. 1 minus half is 0.5. 2 minus 2 minus 7 divided by 2 is minus 5.5. And then the last row, I've not done anything here, but so it'll remain the same. Okay, I'm not done yet. Remember, there's another step. I need to use the pivot, which is still 2, to eliminate this 2. The next step is actually kind of straightforward. I have to do my new row 3 will be my old row 3 minus, I use the pivot, this one, put it down. This one goes on top times row 1. So that's basically row 2 minus row 1. So that would be the first row remains unchanged. The second row remains unchanged. I'm not modifying it. Okay, now this one would be 2 minus 2, essentially 0. 2 minus 1, 1. Minus 1, minus 1, minus 2. 3 minus 7, minus 4. Okay, that was easy just because it was row 3 minus row 1. Okay, so what you notice is after the first iteration, so this is end of iteration 1, you saw that you eliminated x1 from row 2 and row 3, which was your goal. Okay, next step is would be to eliminate, to use this as a pivot and use that to eliminate this 1 to 0, right? So you go column by column eliminating. So next step, I'm just going to rewrite that expression on the next page. So rewriting it. This is iteration 2. If you want, I can write here iteration 1. Iteration 1. iteration 2. I'm just going to rewrite that expression. So what I got from the previous iteration was 2, 0, 0, 1, minus 3.5, 1, 1, 0.5, minus 2, 7, minus 5.5, minus 4. Okay, now I'm going to eliminate this one using this as the pivot. So new R3 is the old R3. This is R3 minus, I need to divide by 3.5, negative 3.5, and multiply with 1. That comes here, times row 2. 2, 0, 0, 1. Everything, the first two rows remain unchanged. So now this one would be 1 minus 3.5 times 3.5. So I just, that's pretty much a 0, right? Let's write it 0. Make some space here. 1, 0.5. Okay, now let me write that down step by step. So this will be row 3 minus 2, old row 3, minus 1 divided by minus 3.5, the pivot. Okay, I wrote this as it is, times row 2, so 0.5. So 7 remains as it is, minus 5.5 remains as it is. Then I have minus 4 minus this thing, 1 divided by minus 3.5 times this 4. Okay, again, you can crunch these numbers through a calculator, and you get 0.5 minus 1.857, 7 minus 5.5, and that comes out to be minus 5.57. Okay, so we see that in just 2 iterations, we have basically got it in the form we care about. There's zeros here. It's in the what they call the upper diagonal format, upper diagonal format, which means that anything below the dotted line here. Yeah.
For the one that you're writing right now, shouldn't that be negative 4 minus 1 over negative 3.5 times negative 5.5?
Oh, did I miss? Yeah, I did a mistake. It's a good catch. This should be negative 5.5 because it's row 2, which is this. Thanks. Yeah. So you see, it's in upper diagonal format. We don't care about this part because that's the right-hand side. Okay, now what's left is to back substitute. This is just saying that the equations now are in this format. Minus 3.5. And then minus 1.857 x3 equals. So clearly from the last equation here, we can solve for x3. It comes out to be 3. Now we put this 3 in the so let's call this A, B, and C. Put C in B. So we have minus 3.5 x2 plus 0.53 equals minus 5.5, and that can solve for x2. It comes out to be 2. And then put x2 equals 2, x3 equals 3 in A, and you can solve for x1. It comes out to be 1 actually. Yeah. So these are my answers. X3 is 3, x2 is 2, x1 is n 1. Okay, I went very slowly on that, but I hope that once you solve one or two problems, you can get pretty fast with solving this.